Hello everyone. We are going to discuss analysis of electrical circuits using graph theory. This is the application of graph theory in network analysis. So let's begin. Okay, so why to use graph theory for analyzing electrical circuits? There are so many other methods like mesh analysis, nodal analysis, source transformation, etc. So why to use graph theory? Here we have given a little complex network that you can see. If I tell you to solve it using pen and paper, would you like to solve it? The answer is no. Instead of that, I give you a program in which you have to draw the circuit and program gives you all the parameters. Then it is obviously a better way if we can have a program to solve the circuit. Graph theory provides a programmable and systematic approach to solve the circuit. Here, all points are listed which I have discussed in the previous slide. Now let's understand the process of analyzing circuit step by step. Okay, so first step is construction of network graph. We will see how to construct a directed graph from an electrical circuit. For that, first we have to short circuit all the voltage sources and open circuit all the current sources. After that, the resistors of the electrical network will be the branches of the directed graph and nodes of the electrical network will be the vertices of the directed graph. The direction of any branch in the graph will be the direction of current in the respective resistor. For example, if this branch represents R4, fourth resistor, the current in R4 is from node 1 to node 2, then the direction of the branch 4 will be from vertex 1 to vertex 2, and so on for every branches. Here, direction of current in every resistor is assumed randomly. Next step is formulation of incidence matrix. Incidence matrix represents the network graph mathematically. Rows of the incidence matrix represent nodes of the graph and columns of the incidence matrix represent branches of the graph. Let's construct its first column. Here you can observe that branch 1 is connected between node 1 and node 4. Its direction is towards 1 and away from node 4. By convention, if the direction of a branch is towards a node, then corresponding element will be minus 1. We can observe it here. Direction of branch 1 is towards node 1. So the corresponding element is minus 1. And direction of branch 1 is away from node 4. So the element for branch 1 and node 4 is 1 and other elements are 0. Let's do it for branch 4. Branch 4 is connected between node 1 and node 2. Its direction is towards node 2. So the corresponding element for branch 4 and node 2 is minus 1 and element that corresponds to node 1 and branch 4 is 1 and other elements are 0. The next thing you can observe from incidence matrix that if we take summation of elements of every column, it is 0. Minus 1 plus 1, 0. Minus 1 plus 1, 0. It is because every branch is connected between two nodes. If it is going away from a node, then obviously it is coming towards another node. So, for a column, if there is a minus 1, then obviously there is a 1 because for a node a branch is starting and for a node a branch is ending. Or we can say that it is coming towards the node or it is going away from the node. So we can observe that the summation of elements from every column is 0. So if one of these row is not given, we can calculate it from other 3 rows. For example, if node 4 is not given, we can calculate it from row 1, row 2 and row 3. Let's calculate it here. Here we can observe that there is a minus 1, so there must have a 1 so that summation can be 0. So here the element will be 1. Here the sum is already 0. So the element in the row 4 must have to be 0. Here sum is -1. So the element in the fourth row have to be 1 and so on. So we can say that it is sufficient to have number of nodes minus 1 row in incidence matrix. So this is our final incident matrix that represent this network graph. Next step is formulation of network equations. In this slide, we will formulate KCL equations. The current from the branches are represented by small I. For example, the current from branch 1 is I1, the current from branch 4 is I4 and so on. Now let's apply KCL at node 1. So the equation will be minus I1 plus I2 plus I4 is equal to 0. Let's apply KCL at node 2. Equation will be minus I4 minus I5 plus I6 is equal to 0. At node 3, equation will be minus I3 minus I2 plus I5 is equal to 0. So these are our 3 KCL equations. If we want to represent it by a matrix equation, we can represent it by this. Now let's do matrix multiplication. Minus I1 plus I2 plus I4 is equal to 0. This is our first equation of KCL. Then minus I4 minus I5 plus I6 is equal to 0. This is our second equation of KCL. Then minus I2 minus I3 plus I5 is equal to 0. This is our third KCL equation. So we can say that this matrix equation represents all 3 KCL equations. Now we can observe that this is our incidence matrix that we have formulated in previous slide, and let's say this is the matrix I that represents all currents in a column. So A is the incidence matrix and I is the current matrix of a network graph. So AI is equal to 0 is the final KCL equation that represents all KCL equations of a network graph that will be used in later slides. Now let's formulate KVL equations. In the graph, nodal voltages are represented by small e and branch voltages are represented by small v. Direction of branch voltage is taken in direction of branch current. Let's derive relation between nodal voltages and branch voltages. If we assume that node 4 is grounded, then E4 will be 0. Then V1 is equal to E4 minus E1 is equal to 0 minus E1 is equal to minus E1. V2 is equal to E1 minus E3. V3 is equal to E4 minus E3. V4 is equal to E1 minus E2. V5 is equal to E3 minus E2 and V6 is equal to E3 minus E4. So these are our 6 KVL equations. If we want to represent these equations by matrix form, then we can represent it by this matrix equation, which is V is equal to A transpose E. Here V is equal to column matrix of all branch voltages. E is equal to column matrix of all nodal voltages, and A transpose is the transpose matrix of our incidence matrix. If you do matrix multiplication and then assignment, then you can get these 6 KVL equations. So this is the final equation that we will use in later slides that represents all 6 KVL equations. This figure represents a generalized kth branch of network. Voltage across this branch is Vk and current through this branch is Ik. Value of voltage source in kth branch is Vsk. If it doesn't contain voltage source, then Vsk is equal to 0, otherwise it will have some value. Value of current source in kth branch is Isk. If it doesn't contain current source, then Isk is equal to 0, otherwise it will have some value. Value of impedance in kth branch is Zk. Here value of resistance is Zk. Here impedance is always resistance. We can observe that Vk is equal to voltage across this voltage source plus voltage across this resistance. So Vk is equal to Vsk plus voltage across this resistance. By Ohm's law, voltage across this resistance is equal to current through this resistance into Zk. Current through this resistance is Ik minus Isk. So the voltage across this resistance is equal to Zk into Ik minus Isk. So Vk is equal to Vsk plus Zk into Ik minus Isk. Now let's make Ik the subject of the equation. We will get Ik is equal to Vk minus Vsk upon Zk plus Isk. Let's say 1 upon Zk is equal to Yk. Yk is the admittance of the kth branch. Here it will be 1 upon Rk. Rk is equal to resistance of kth branch, and here Rk is equal to Zk. So Ik is equal to Isk plus Vk minus Vsk into Yk. Okay, so this is the equation which we have derived in the previous slide. Now we want to make this equation generalized so that it can represent the equations for all B branches of this form. For that, we will need some matrices to be defined. Here, Vs is the column matrix containing the values of voltage sources for all B branches. Is is the column matrix containing the values of current sources for all B branches. Y is the diagonal matrix containing the values of admittances for all B branches. Here dimensions are taken B cross 1, B cross 1 and B cross B so that matrix multiplication can be possible in this equation. Now let's replace Ik with I, Yk with Y, Vk with V, Isk with Is, Yk with Y and Vsk with Vs. We will get this equation. If you do matrix multiplication, then matrix summation and then assignment, you will get B equations of this form for all B branches. Okay, so this is the derived equation. I is equal to Yv plus Is minus Yvs. Let's multiply incidence matrix at both the sides of this equation. We will get Ai is equal to Ayv plus Ais minus Ayvs. We have derived KVL and KCL in the previous slide. That says us V is equal to A transpose E and Ai is equal to 0. Let's put these values in this equation. We will get Ai is equal to 0 is equal to Ay A transpose E plus Ais minus Ayvs is equal to 0. From this equation, we will get Ay A transpose E is equal to Ayvs minus Ais. In this equation, all the matrices except E are known. We know the values of matrices A, Y, Vs and Is. So from this matrices, E can be calculated. E is the matrix of nodal voltages. Okay, so from this equation, we can calculate nodal voltages. Once E is known, we can also calculate V as V is equal to A transpose E. And once V is known, we can also calculate I from this given equation. Okay, so we have calculated nodal voltages, branch voltages and branch currents. Okay, so all the network parameters are calculated using graph theory. Okay, so can we use this theory to make a market product? Yes, we can make a software which analyzes large and complex circuits using this method. The small example of MATLAB program is given in our website, and the link of the website is given in the description box. For more information about this topic, please visit the website. Thank you.